You can't even see it.
Oh, all right. What's not complete circuit? Oh, you mean that? All right. Hey, it's past time to get started, so let me go ahead and get us started. And I'm going to start with a question that I want you to think about, and maybe we could come up with a consensus, or maybe it should simmer for a while, and I should ask you again on Thursday. But it has to do with our calendar and where we're headed from here. As you know, we've been doing a lot of electric fields. We're about to switch over to magnetic fields. And our next test is a little bit of ways, but it's coming up. Here's the calendar of the breakdown. Today is October 15th right here. And in 2 weeks and 2 days, your next test is scheduled. So don't panic yet. You can panic tomorrow, but the test is coming up. And we've done 2 chapters. We've done, or in the middle of our second chapter, or more than middle, we're almost done with this chapter. But the point I'm getting at is the schedule kind of has us wrapping up this chapter 28 really Thursday, but I haven't got a chance to do any examples. And there are a few more things I'd like to show you that I think would be to your benefit. But if I do that, that means we won't be starting the next chapter on magnetism till Thursday, which means that it might be a little tight schedule getting those 2 chapters accomplished before the test. We still could. This is what I'm kind of struggling with, is that what I kind of would like to do is the following, is I'm thinking that today might be best spent on circuits and lots of good examples from the circuits and some more demonstrations to show you. I brought the magnetism just in case, because if we do all day on circuits and we don't really start magnetism till Thursday, then this first chapter on magnetism would fit here, and our second chapter would fit here. But what that would mean is we are finishing the second chapter on magnetism, which would be chapter 30, which is a pretty hard chapter, and then we have the test in 2 days. And so I was kind of thinking that might not be the best plan, and so if we bump the test to the following Tuesday, that would allow us to finish a hard chapter 30 here, give it a week to kind of simmer and sink in. On the 31st, we would probably then start the next chapter, which would be 31, Faraday's law, then, and have the test here. And so that would give me a chance to show you some neat things today that I'll otherwise skip, and then bump the test to here, have the review on the weekend. And I wanted to know your thoughts, because I don't know what your math schedule is. That's the big thing. Your math schedule, your, so, any... On the 5th. Ah. So that's not a good idea, is what you're telling me.
Halloween's on the 31st.
Well, okay. Back to the Halloween. True, this is Halloween, but the test on Halloween, at least my experience in the past, has not been the big issue. It's the day after Halloween. So it is that morning. So Halloween doesn't begin till later in that afternoon. So I don't think the 31st is a problem. But the 5th does sound like a problem. On the yeah, bummer. Okay. Good to know. Okay. And just kind of a straw vote right here, and I'll think about it and talk to Don and see if I can come up with something different here for Thursday. But of those of you who are here, who would say the 5th is a bad idea? A bad idea because of your math and whatever. And a chem exam on the 6th. Okay, all right. So there's a lot of you. All right. Huh? Yeah. Yeah. Oh, well, okay, but the review is tied more to the test date than anything else. Yeah. So, but the 5th is not a good idea. All right. So I'll tell you what. Let me keep rethinking about this. And
you didn't ask about the 31st.
oh, okay. Well, what do you want me to ask about the 31st? Who says the 31st is what? Good idea or bad idea? Bad. Okay. Who thinks the 31st is a bad idea? Well, but I guess I should ask why you guys think it's a bad idea.
We have tests on the 31st.
Oh, you have other tests on the 31st? What test? Is that 220?
That's easier though.
That's easy. All right. Well, who has? I guess it's differential. Who has tests on the 31st? You don't count, but who has tests on the 5th? Okay. The 4th, is that what you're saying?
200 and 210. You can't help everyone. Like, you can't help everyone.
Really fast at the end, where, really nice. Like the last, like we had our...
No, because we would just start the next chapter on the 31st. Yeah.
It wouldn't really affect the overall...
No. You got a suggestion, Dave?
Why not the first? Why not the first?
A test on the 1st? Well, we can't have a test on Friday. Well, it's not a scheduled class day.
What about the 7th?
I mean,
I think 5th is okay. How are we going to grade based on the attendance?
Okay. Move it up a day? To 29?
And we can all make the review on the weekend. And Halloween will be
Well, somebody mentioned the 7th. Would that make things better or worse? The 7th? Worse? All right. Well, I'm not seeing a easy answer here, which means we might have to leave it where it is then, unless I come up with something better.
so much better.
Yeah. All right. Well, I'm glad I brought it up. Disappointed that there wasn't a good consensus. Sounds like your math tests are spread out over those weekends, depending on which one, or those 2 weeks, depending on which one you're.
A lot of people who have the math test on today aren't here right now. There's a math test today as well. So they're like, stayed up all night studying.
Yeah. Well, and that's mostly why I don't want to make a decision here right away. So I'm not going to make a decision. And if it's too complicated to change it, I guess we'll just have to go with the default. The default is what it's been set at since the beginning, and we'll leave it there. Meanwhile, we better get started with the class, so at least I can show you. Maybe I'll I'll just play it out. There's still some neat things I want to show you, so I'll just do that. And if we get started with magnetism, great. If we don't, I'll give this some rethought and we'll see where it goes from here. But here's where we left off. We did left off with this circuit here. And so I want to throw that back out there. We did a bunch of math. We did it kind of quickly. Let me not repeat the math, but at least let me start with the equations and give the answer. And I wanted to emphasize last time, and I think I got this across here, that if you put the switch in this position here, you would say you are charging the capacitor. What would happen then if you set this at, say, about 5 volts, and I think this morning when I was playing with my power supply, I set it at 5.5 volts. No, 5 volts. All right, so 5 volts. And so let's hook this up again, just like we did at the end of last class, is we said, okay, let's do this. Let's take a wire and hook it to our switch. Now at this point, I'll just put the switch in the up position so it doesn't make any complete circuit quite yet, but I can take my switch and go to the capacitor, and then from the capacitor to the light bulb, and then to the light bulb back to the power supply. And so I made what I'd call the circuit of the big loop here, across and around there. And I'm hoping you can kind of see that. I mean, obviously part of my plan here is so that if you watch me hook it up, you will be that more sophisticated and that you'll be able to hook it up when you get into lab. I know that the wires are kind of hard to see up here, but this other wire would be nice to put right here, which is where the resistor, which in this case is the light bulb, ends. So right there to the other side of the switch. One additional piece that we did not do last time, I thought it would be nice to throw in here as we do the math, is to take, let's take a voltmeter and put that right on the capacitor and say, all right, what do you think will happen when I close the switch? And we saw this equation. We wrote out the equation that said if you take a Kirchhoff's loop rule here, a conservation of energy, and you go from across here, you would get a voltage of V. You would then decrease by the voltage on the capacitor. You would then decrease by the voltage across the resistor. You would get all the way back. So around the big loop, that is the sum of our voltage. We did a bunch of math and we solved this by saying the charge then would be Vc 1 minus e to the minus t over tau, where tau was the resistance times the capacitance, what we called the time constant. Maybe more specifically, the RC time constant. And so this capacitor should be building up charge. A graph of this would look like this, where if you had charge building as a function of time, it would reach a maximum of V over C, but it would start at a value of 0 and increase that. And then that was the closing lesson for Thursday, a charging and discharging, capacitor. And so, if I close the switch here, you will hopefully see, there we go, good contact. You will see the light bulb go on, current is now flowing, the capacitor is building up voltage, and I put the meter up here this time so at least those of you who are close enough can watch the voltage. It is building up and it'll eventually build up, to my case, to 5 volts. And so the charge is building. And right now we are at almost 2 volts. So there's 2 volts. And of course, at 2 volts here means that there's only 3 volts left for this one, and so the light bulb is a little dimmer than it was a moment ago. I suppose now it's probably up to close to 3 volts. Yep, there's 3 volts, and so this voltage here is at 3, which means there is only 2 volts here, which of course means there's less current. And so the current changes with time. And so we took the derivative of this and said the current would start as a V over R and decrease. And so we had this equation, V over R e to the minus t over tau. Well, again, tau is the resistance times the capacitor. And so that was this idea of a charging capacitor. We then can throw the switch the other direction. If we throw the switch the other direction, we then have the voltage on the capacitor minus the voltage on the resistor gives us 0. And in that case, what we had is something that looked like this, where the capacitor then started with a certain charge, Q, which in this case, if we let it charge all the way up to 5 volts, we could calculate what the charge is that it starts with, but then it decays away. And so we had Q as a function of time is equal to whatever it starts with, which maybe I'll call it Q naught, and then e to the minus t over RC. And so we had this charging and discharging capacitor. I think by this time it's completely charged. We are almost at 5 volts, just a hair under. There's still more charge barely coming on, so much though that the light bulb, you can't see it lit anymore. And so if I switch it over to here, hopefully now you will begin to see this part of the equation where the capacitor now is discharging. And the current is now coming off here and running through this connection and going through my resistor. And so at first there was a lot of current and the light bulb was really bright. Now it's dimmer and has gone down to about 2.3 volts, and so the charge is coming off and it's getting less and less and less and less. Yes?
The current output is 0?
I guess it approaches 0. Well, it's one of these things where mathematically you would say it never gets to 0. But remember, don't. And eventually it is going to be 0. Yes. Eventually going to stop.
Why does it take more time for the capacitor to charge up than it takes it to discharge? Mathematically, I
Oh,
how
no.
that process.
No, I don't think it does.
It took it a while to charge up, but now it's just almost discharged in a matter of seconds.
I mean, I guess we could ask, how long would it take to get half charged? And I think it's the same thing. I know there's a slightly different formula here than here. But if I were to say, how long does it take for this to get half charged, I might go Q naught over 2, or excuse me, in this case, half discharged. Then that would cancel off. I would then have the natural log of 1/2 equaling a negative t over RC. If I take the negative off of here and put it in front and then flip that over, I get a natural log of 2 equals to TRC. So I would say that's how much time it takes to get half of its charge off. Maybe I'm missing something here, but I think that's the same time here. Let's see. How long before it gets to half of its full charge? Well, its full charge is the V times the C. So working on this equation, I would have V over C over 2 equals V over C1 minus e to the minus t over RC. Oh, go ahead. Go ahead. Sure. Sure. Oh, you know what? Maybe it was and maybe that was a bad choice on my part, a half. You bet. Because this, if I move over to here, e to the minus t over rc, 1 minus a half is a half. And that's going to be the same number that it takes to get to half. But I wonder if there was a coincidence here. I don't, maybe I should have said, how long does it take to get to, how about most of its charge? So how about 90%? So if I wrote this as 0.9, what would change here? I guess we would have 0.9 there. And so then I would have a negative RC ln of 0.9 is equal to the time, right? And that actually might, is that a little different? That might be a little different. How long does it take to get to 90%? 90% of VC? Oh, yeah, I blew it here, right? This should be, it's discharging, so I want that to come out to be 0.1. Oh, but then that's the same. Yeah, no, so yeah, so it is the same. Good question. I thought it was the same, and I'm sorry if it looked different to you, but I'm pretty sure mathematically it comes out to be the same. There also can be other things in this circuit that aren't represented in this number because there is some resistance in this capacitor that they play funny games with. So you may actually be noticing something that is real that is not represented by these equations. But in these equations, they should be the same. Yeah. All right, well, what I wanted to do then is to take this one step further, in part just to show you a little bit more about capacitors, but also in part to introduce you to this guy. This is an oscilloscope. And I'll turn on the overhead, but you aren't quite there yet in the lab, but you have a lab coming up in a few weeks that says, what is an oscilloscope? How do we use it? What good is it? And it does some neat things. And so this, I thought, would be a good chance to show you a little bit more capacitors and also to show you an oscilloscope. Here's what it is. It's got a lot of buttons and a lot of computer stuff in it, but basically it boils down to a graph and a display. Here it is. On the vertical axis, it measures voltage. On the horizontal axis, it measures time. And that's really what I want to get across to you today. An oscilloscope is a little machine that measures voltage. And then on the horizontal axis, time. So if the voltage changes with time, you can see it. And that's what we have here, right? We have voltage or charge changing with time on those capacitors. And so we should be able to see on this graph this pattern. And so, if you look at this, it is what we say set at 5 volts per division. Right now, I got a line going across here. There is nothing hooked up to it. And what that means is the voltage is 0. All the way across. This right here represents how much time each division is. And so 250 microseconds is plotted across here. And so this computer is just measuring the voltage for 250, 250, 250, 250, 250, 250, 250. So for 2,500 microseconds, it measures the voltage. Nothing's hooked up to it, so it reads 0 and it starts again. Then it just says 0, 0, 0. And that's all we have. But I can change that. I can change that by hooking up something that does change with voltage. And so if I take this little box here and say, watch what happens if I send a voltage that changes with time. And so I'm going to hook this up, maybe make a quick adjustment, do something like this. And so before class, I adjusted this box that what will happen is the voltage will go up, down, up, down, up, down. And it goes up to here for, it looks like a little bit more than one division. I will call it still roughly 250 milliseconds. It looks like it's a little bit more time than that. But for roughly 250 milliseconds, we get a voltage, then we get no voltage. Then we get voltage, then we get no voltage. That would be like me standing over here with this little switch, turning it, holding it there for 250 milliseconds, pulling it back, discharging for 250 milliseconds. And just go back and forth, back and forth, back and forth. And so the reason I'm showing you, yeah?
I thought you said the center was 0.
Oh, okay, you're right. Feel better? Okay, so it goes on, off, on, off, on, off. Okay? But remember, 0 voltage is just a reference. So it's going to go charging, discharging, charging, discharging. Whatever 0 is just kind of my reference point. So I'm going to adjust it so that the 0's there.
Is the 5 volts the maximum volt?
Oh, now I've got this set at a lot more than 5 volts because you can see that this says 5 volts per division. So this goes up 5, 10, 15, 18 volts. So it goes up to 18, then down. 18, down.
Why 18?
There's nothing magical about the 18. Shall I turn it down to 5? Do you feel better? How's that? Oh, still too much? Is that what? So again, nothing magical about that. Now this one I always set at 5 because this capacitor is not supposed to go over to 5. But I'm going to use these capacitors which can handle 50 volts. So say that again, 1.7 there?
What's that mean?
Oh, that's... Oh boy, how do I explain that one? This is what they call the trigger. This is the computer looking at how does it want to draw this pattern, and it's going to put, when this is at 1.7, right in the center and spread out. So it's more of a display issue. It's yeah. So more on that in the lab. Let me not get into that today. Yeah.
How come it's shown as a standing wave? Why is it? Because the first graph that you showed us, it was sort of like moving, but then now it's a standing wave after you adjusted it.
Oh, okay. So the point I'm trying to get at is this machine. Let me turn the voltage up a little bit here, okay? The point I just want you to see is this little box just turns the voltage on, off, on, off, on, off. That's what I want you to see. It would be like me throwing this switch back and forth. At that end, I just want to kind of give you a heads up on a little fancier equipment that is kind of hard to understand that you're going to see, and the more I bring it out, I think the better off you will be by the end of the semester. Now, as far as the visual effect, then the computer on here, since this goes on, off, on, off, on, off, okay, if I did something like this, here's why that looks unstable. It looks unstable because what is happening is it goes on, off, on, off, on, off. When it gets to the end, it starts again. It may not start in the same place. And so if it doesn't end exactly where this one began last time, then when the next time it draws it, it's going to draw it at a different location. And so what it'll look to you like is like it's fluctuating or changing. And that's not really what's happening. That's just a display of it. So in order to adjust that, which is what you're talking about, this number here, I can tell the computer to measure the first time. And when it gets to the end, don't automatically start displaying the next one. Pause until the voltage that it was on the first display gets back to the same place as it was before. So that way, unfortunately, there's a little delay then between the end here and starting again. But the good thing about it is it'll start in the same place. And so if the machine has the same pattern, it won't look so unstable. And so we call that its trigger effect. And that's that. And so that's part of the technique of learning how to use this machine. And we will do that in the lab. But for today, fair enough. This is just a switch going on, off, on, off. That's what I want you to see here at the beginning. So I'm going to disconnect it here. Okay? And hook it up then to just something very similar to this. And so I can hook up the feed to a resistor, and then get this one out of the way. From a resistor, if you remember your resistor boards from lab, to a series of capacitors. I'll start with the small capacitor, and then here. And so I hope what I have up here in front of you is, although it's not hooked to the meter yet, what I have is on, off, going to an RC circuit. If I then look at the voltage on this capacitor, I'm hoping you will see what I'm after. Remember the on, off, right? Can you kind of see that right here, this is the charging of the capacitor? And then it fully charges. And then it discharges. And so hopefully what you see is charging and then discharging. Charging, discharging, charging, discharging, at a much faster rate than obviously I can do by hand. But I thought this would be a good opportunity not only to see it, but watch what happens when I change the capacitor, right? What does this C mean? This is the rate at which it charges up. And so what if I were to increase the capacitance? Yeah, that means this number is bigger. That means it takes longer to charge up. So I'm going to switch from this bottom capacitor, which is our small one, to our medium-sized one. And what do you see now? Yeah, you see that now it doesn't completely charge up. You kind of see it getting formed and beginning to arch over. And so we get maybe right about here. And then this starts. And it starts to discharge. And it probably doesn't get a chance to discharge all the way because it's a bigger capacitor. And so we go from charging, discharging, charging, discharging, charging, discharging. What do you think it might look like if I went to the next capacitor, even bigger still? Yeah, it would probably not get even to the arching part here. And so I will go to the larger capacitor. Well, and you get a little bit to the arch there, and you can see it begins to charge up, and so it gets to maybe right about there, and then it begins to discharge. But it doesn't discharge all the way. That's why you only see it from about there to there. And so it charges and then discharges and charges and discharges. And of course, what I wanted you to see was not only the shape on the graph, but also how the oscilloscope works, but also to point out this is yet another good use of a capacitor. I forget how many we've done now, like 3 or 4 good examples, and I want to show you 2 more today. This is what we call a timing circuit. I can hook up my capacitor and my resistor with a certain value that how long it takes to charge up or how long does it take to discharge is a function of time. You notice it probably the best with the remotes on your car. Have you ever gotten out of your car and locked it? You will probably know that the lights go on, and then what? They're on for a short amount of time and then dim and go off, don't they? And so the electrical engineers have designed a little RC time constant. They've adjusted it so that the time that it takes to discharge is, a couple seconds, so that the computer knows, okay, somebody hits the lock button, take a few moments to leave the light on, then turn it off. The dome light is probably a lot like that. Last night, I was getting out of the car thinking about it. I had the door open and I closed the door. And as I closed the door, the dome light was on for a couple seconds, and then it would dim, 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 and off. And so clearly they had used a timing circuit, an RC timing circuit, and took advantage of controlling how much time that little dome light should be left on. So unlocking, locking, all these little timing ones are really nice little timing circuits. So watches don't usually use these anymore. They use a quartz crystal to keep track of time, but certainly many time circuits are used this way. How long between flashes in your blinker? How long does the blink go on the blinker? All of these things that are a controlled amount of time are a combination of the RC, and that's what I wanted to give you some value added. So yes, we're learning the physics of it. No, this isn't quite a circuits class, but hopefully you will take with you the application of this, and you'll see why you're bothering to study the physics so that you can actually apply it later on. Yeah.
If 250 milliseconds were increased, then we see more of the arches in the...
Oh, yeah, so if I were to leave it on longer, up this way, on longer in time, you would see it does get a chance to fully charge up. If I give it less time, well, that's as far as that setting will go. You'll see less of the charging. Again, good example, good question. All right. Did I see another question? Right. Yeah.
Sometimes in like cars that have been in accidents, their blinkers go a lot like really fast. Is that just like maybe a damaged circuit?
Yeah, so something's probably damaged in the circuit, but I'll even go one step further. You may know this if you hook up a trailer. And so what ends up happening is in the original car design, you had a capacitor and a resistor, and the resistor was probably the resistance of the light bulb. And then you hook up a trailer, and to run the trailer lights, you tap into those lights. So now you have two resistors in parallel. You have the light on the car, and you have the light on the trailer. Those two resistors are equivalent to a smaller resistor. Now you have a smaller resistor, that's going to change your RC time constant, and so when you turn on that blinker, it starts going dink, 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 instead of the dink, 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 dink. Yeah, exactly. Yeah.
On my motorcycle, the blinkers are LED versus incandescent. Do the LEDs take up or have a different resistance? Because this blink faster.
Yeah, and so their time, well, I don't know for sure what they are doing, but I would probably guess that they are not using then the resistor of the LED to make the timing circuit. So they have another resistor added in there to make the timing circuit, and then that then controls maybe a transistor which does the blinking for your LEDs. Yeah, that would be my speculation on that. Yeah. So good point. I mean, once you get to LEDs, you can't use the resistance of the light bulb anymore. Yeah, yeah. Well, like I said, I thought that would be a good opportunity to show you the RC time constant, but I also thought it might be a good opportunity to try something like this. This is kind of neat to see. Let me just kind of disconnect all these wires and throw my resistor board over there for just a second. Let me lay out my wires. Let me come back to this oscilloscope again and hook it up so you can, again, kind of see what's coming out of this box. Maybe I'll put the timing back to, actually I'll go right there. That seems to be almost dead on to the 250 microseconds here. But let me change this little box, and instead of going completely on and completely off, it varies in more of what we would call a sinusoidal signal. So the voltage increases, the voltage decreases. But again, if you're getting the main point of what is this box, it's an oscilloscope, you can see that it is plotting the voltage as a function of time. So this little machine puts out voltage that changes with time. Both of these little boxes we will start using a lot in lab. Okay? Now, if you'll notice, I have a second little box. Let me turn it on and plug it in up here. Now I set this box a little bit different. This box is designed so that it has voltages that just kind of spike up real quick with time. Just, and it's no voltage, then spike. No voltage, spike. Okay? And isn't that what you see? What if I put the two together? What if I were to take the top one and the bottom one and hook them together? Now, if I hook them to my oscilloscope, I'm hoping what you will see is you will see a combination of those two. You will see the sinusoidal pattern with a bunch of spikes on it. Okay? Now, visually, it's going to be hard to see because the computer on here just goes through, and this goes to your question, and it displays it. So let me add one more feature, which I won't quite explain yet, but so that I can see it and you can see it a little bit better. Let me just make some adjustments and say, all right, here is what these two boxes together are doing. The first box is making kind of this sinusoidal pattern. The second box has these, what I'll call noise. These maybe unwanted voltage spikes that I really don't want. How do I get rid of them? Yeah, and this is a good example of a capacitor. Remember, the capacitor takes a while to charge up. And so these quick spikes may not be enough current to charge up one of these guys. And so those spikes are doing nothing more than charging this. They never add voltage. And so another nice feature of our capacitors is they can be used as filters. And so if you have what we might call a noisy line and you hook it to a small capacitor, you probably will see very little effect. I think we saw there was a little, wasn't there? And it kind of reduced it. But if I hook it to a large capacitor, I will have cleaned it up a lot. I will have filtered it out. And so another really nice use for these capacitors are filters. And that's why I thought I'd take a little extra time and show you that. Because we are eventually building up to that, yeah.
Wouldn't that eventually charge the capacitor?
Oh, but it's going to discharge. Because it goes up, down, yeah.
Oh, okay.
Yeah. So that's the nice thing about having capacitors and alternating currents is what we'll call it. All right, well, I hope that wasn't too much time to take away from really the last part of the chapter and the examples. But I thought it would be good to see, because I know that I get more encouraged from studying my math, my science, my engineering, when I begin to see, why do I care about this? What the heck are these capacitors for? And of course, it was easy at the beginning when I did the capacitor for the first time to show you, oh, you can think of it as a tank that stores energy. That's a good first example. But the truth is, capacitors are used far more for things like this, timing circuits and filters, than they are for just storing the energy for when the power goes out.
They're used for filtering audio, right, and audio equipment?
Exactly, that's what I just did, right? I filtered out, maybe in this case, the high frequencies, right? And so if you're familiar with audio equipment, you'll often have equalizers where you adjust the thing and you say, okay, what I want to hear is just the basses. And so you adjust it so that the high frequencies don't come through. Or you adjust it the other way, just the low frequencies come through, or, whichever. Yeah. And, yeah. So, yeah, really good examples, yeah.
Same with the Cox Internet. One of the day the technician came out and he hooked up this filter with a big battery looking thing and just capacitor.
Yeah, it might have been a little more than that, though. I have a feeling it was not only a capacitor for a filter, and it could have been all it was. But it might have also been another type of filter called an inductor, which we will get to first. And I suspect it was a little bit of both. So what we would call an LC filter, an inductor and a capacitor. So we'll see that in a few weeks. Yeah.
So do radio filters work on things?
Oh, good point. Yes. In fact, I should have brought it out again. You might have remembered that when we first did capacitors back in chapter 26, I had a big one where you could see the plates move when you turn the knob. And I said this came out of a ham radio, and as the plates overlapped, you got a different capacitors. That came out of a ham radio, and it was used as the tuning circuit. It could tune on what channel you wanted to receive. And so by turning the dial, I can listen to different stations. You do the same thing on your TV or your radio. You change it from, one capacitor setting, which may get, K-tide, 99.9, and then you get tired of that, so you go to 95.9, when you kind of go over, and you get a different capacitor, which is a different filter, which allows a different frequency. And in that case, you only want one frequency or one channel. And that's what's going on inside of the electronic box in order for you to decide what radio channel or what TV channel. You hit the remote, and you go from channel 2 to channel 3 to channel 4, and you're changing the electronics of it. And usually it's... What? It depends how sophisticated the electronics is. Yeah. So anywhere from 1 to thousands, but the thousands are probably integrated in a circuit. So the electrical engineer probably just buys the circuit from Motorola and say, hey, I want a tuning circuit, and I'm going to put this into the radio. Okay, so I better move on here. There is one last thing, and I really want to do some examples here for you out of the book. I know I did some good examples that weren't in the book, writing out the equations, and particularly solving the matrix. But, and I'll probably end up doing more of those when we do examples here from the book. But your author actually has one more thing. Your author actually did it at the beginning. Some of you already asked me, he goes, wait a minute, you haven't even talked about the internal resistance of the battery, the very first section. And you're right, I hadn't. I was saving it towards the end, and I got a little behind time, so I wish I would have had talked about it last Thursday so that you would have had all of that done over the weekend and you wouldn't have questioned whether I skipped it or not, because I was planning to come back to it. And I think it's easier to talk about the internal resistance at the end of the chapter as opposed to the beginning, but that's the way your author has it. So some of you have already seen it at the beginning of the chapter. We did a lab on it, and here's how I want to describe it. We're going to take a new look, and I say new, but we already talked about it in lab, and so let's take a closer look at a battery and its internal structure here for just a minute. Because as many of you probably recall from lab, that we described our batteries, and you did a lab, not last week but the week before. You said, look at a new battery and look at an old battery. You remember working with these in lab? And whether it's an old battery or a new battery, when we get inside, and so here is a big one of these. In fact, here is one of that size cut. And so if I take one of these and I cut it open, but let me go to a little bigger size for a classroom like this. So let me take this battery and cut it open. I'm hoping for a big class like this, you guys can see the metal zinc on the outside and the carbon on the inside. You can obviously see the black. That's mostly the carbon. And along the outside, you might see the white flakes of where the carbon has reacted with the zinc. And there's kind of that edge. But what we're going to do, and not the chemistry. Many of you are in chemistry, that's good, and so hopefully you probably have some good questions about the chemistry of it. But without getting into the chemistry of it, we are going to say that there is a certain voltage created because of the chemical reaction. We like to refer to that as its EMF. And we give it a script E, meaning the electromotive force. This is how much you get from just from the chemical reaction itself. However, as we tried to point out in lab, and I want to repeat here, is that now that this chemical reaction took place, then the current has to move throughout the material that makes up the battery. And as we already learned from chapter 27, that means there is some resistance. And so batteries have not just an energy source, but also an internal resistance themselves. Not that we want them to have that. And you do everything you can to build the battery so that whatever material it's made out of, which in this case is carbon, has very low resistance. But unfortunately, carbon doesn't have a low resistance, and we need to consider that as part of the operation of our batteries. And so we like to take batteries and think of them as two mechanisms inside. One is the chemical reaction, and the second is what we give a labeling of a little r to say what is the internal resistance. Because when you take then a battery and you hook it up to something, which again, this is what you were asked to do in the lab, and you'll watch me do here in just a second. When you hook it up, and let me just call that capital R, okay? Not to be confused with the little r. As you go to run this object, you've got to then realize that you are not going to get the full voltage of the EMF. You're going to get a small loss internal to the battery. And then, of course, here, this part, this is the energy, of course, that you want to be consumed. So in my case, I would call this my battery with some internal resistance, and it's hopefully a small value because this is a newer battery. And then if you remember this one you used for your old battery, hopefully this one has an EMF and then a large internal resistance. If I use these to run a light bulb, so here will be my light bulb, will I get the same effect? No. What do we mean by a bad battery or a dead battery? And as we tried to indicate in the lab, it's this guy here. And as our battery gets old, it's not so much that we get less voltage from it. It's that we get more internal resistance here. And if we go through a couple of steps in math, watch this. If I do the Kirchhoff loop rule, that's why I wanted to do the Kirchhoff loop rule first. That and the fact I wanted to make sure I covered it last Thursday so that you could do the homework on it over the weekend if you were that far into it. Because I don't think these are nearly tough as mathematically. But as I do the loop, I can start over here and say, okay, there is an increase in voltage. Then here is a decrease in voltage. Then there's another decrease in voltage from my, what I'll call the load resistor. So a decrease, and I get back where I started. So there's the Kirchhoff loop rule, right? Conservation of energy. Go around the loop here. And if we solve this for current I, it doesn't really surprise you that it comes out to be EMF divided by the sum of the two. Because if we were to call it's an internal resistor, you would have looked at these two resistors and said, aren't they in series? How do you get the equivalent resistance? You just add them. And so it's not a surprise that this comes out to be the EMF divided by the equivalent resistance. But what I am trying to point out is the amount of current is dependent then not just on what you hook up to it, but also this internal resistance. And it plays a part, and it can play a major part in the overall operation of your circuit. Yeah.
So is it worth buying electric cars?
Is it worth what?
Buying electric cars?
Is it worth buying electric cars?
Yeah, because the battery could eventually go bad.
Well, Okay, the batteries are rechargeable, so it's not like they go bad and then you have to go buy new ones. But you're right, eventually they only take so much charge. And I guess I would say I think we've crossed that threshold. If you had asked that question 5 years ago, I probably would have said, I'm very skeptical. And the last time I was in a market for a new car was about 2006, 2007. And I wasn't sure the batteries would last long enough to make it worth it. Because if they go bad, you know, you're looking at a huge investment, about $10,000 to get a new set of batteries. So I avoided the electric car back then. But I think we have turned the place, and I think they've been on the road long enough to say that you can get 100,000 miles or more before you have to replace the batteries. So my next car, I'm going to look a lot more serious and probably will get an electric car. I think we have crossed that threshold. Yes, they are going to go bad, and yes, I'm going to have to shell out $10,000 for a new battery, but I'm thinking I won't have to do that till I put $110,000. Huh? Yes, and I like my Ferraris in red. You know, by the way, yeah, it's, who does? Tesla, there you go. So I'll sacrifice the red Ferrari for a red Tesla. There we go.
The old battery and just replace the metal inside, it would just fix it. It would make it. It's not the chemical. It's not the chemical.
Well, yes, and that's exactly what happens when you recycle a battery. When you have a battery like this and it eventually goes bad, you can't just put it on the charger and recharge these. What rechargers do is they run current the opposite direction, and if that undoes the chemical reaction, then your battery is recharged. But not all chemicals undo. In fact, these alkalis are so strong that when they hook together, you're not going to undo them by running current through them. So these are not rechargeable. What we need to do with those is take them and recycle them, and a chemical company will then open it up, as you said, and redo the chemistry with other chemicals and eventually put this material back into a battery.
So with those ones, it's the chemicals, but with the chargeable ones, that resistors.
Well, I should emphasize, no. Those go hand in glove. When you make a chemical reaction, when the battery was charged, the current has to flow through the unreacted chemicals, which usually have a good conductivity. Then as those chemicals react, now you've got to go flowing through a new molecule, which has a different resistance, and unfortunately is a pretty high resistance. So the increase in the resistance does directly tie to how much chemical is left in the battery. Yeah. So those aren't separate. All right, so coming back to here, I just wanted you to see that, of course, the current is changing. And a good model of representing batteries is to say that it's not so much that their EMF gets weaker as you run low on chemicals. But a better model is to say that their internal resistance increases. To prove that, you did a lab on it, and I'm going to repeat that here now. Watch this. I've got what I would call a good battery and my voltmeter. And what you were supposed to notice in the lab is that whether you had a new or an old battery, and so I'll take a new battery and hook it up, and I will get 1.55 volts from what I will call a new battery. If I take an old battery and hook it up, you might not think it's an old battery. Look at the voltage I get. 1.54. It's essentially the same voltage, right? So why would I say it's old? Why would I say it's bad? Because what will end up happening when I hook this up and I try to make some current flow, I'm going to get very little current in the old battery, not because this number is any different, but because this number is different. And I think you can see that well, although this is a 5-volt light bulb, so for you to see it, I'm going to put 3 good batteries in series because they're roughly about 1.5 each. And so if I put 3 batteries in series, I should get about 4.5 volts. So sure enough, I have, for those of you who can see, 4.6 volts here, right? And so now if I take my light bulb and I hook my light bulb here, it should turn it on. Now, not very bright because, you know, like I said, this light bulb is really a 5-6 volt light bulb. But it'll make it run. And so now the current is flowing. And, I don't know if you noticed, for those of you who are close, it dropped a little bit in voltage. Why? How much voltage do I have from, say, here to here, where my meter is? Yeah, notice this would be the EMF minus however much voltage is lost because of the internal resistance. What we called in lab the terminal voltage of my battery. Now these are good batteries. So even though I'm getting a lot of current, enough to make this light bulb go on, the voltage only went down by 0.3 volts. And hence I would say this is a good set of batteries. This is a charged battery. The internal resistance is pretty small. But to illustrate my point, let me replace these 3 new batteries with 3 old batteries. I'll start by first disconnecting the light. And I'll bring that back in a second. But let me replace this new battery with an old one. Let me replace then this new one with that old one. And finally, let me replace with that one. And what I want you to see is what's the voltage now? It's still 4.5 volts. It's even 4.6 still.
They're all dead.
But, as I'm trying to say, these batteries are in the category of dead. These batteries will not work. And when I hook them right now, they seem to appear to be fine. I am getting the EMF of all 3 of those. 1.5, 1.5, 1.5, and a little more than 1.5. So I get 4.6. And if that's all I did, I would think, oh, this is a fine set of batteries. But to illustrate this, what do you think will happen when I turn on the light? When I actually plug in the light here? And the current begins to flow. The amount of current is not just the EMF, which I'm still getting the same EMF, whether it be an old battery or a new battery. It's that this number is so big. This number is so big that the amount of current I get will be very, very small. And I highly doubt you'll even see the light go on. Let's see what happens. And, maybe I should point out, not only will you not see the light go on, but because the internal resistance is so much, you will see now the terminal voltage significantly drop. And you'll see why we would say this does not work. And so I'm going to take my light bulb and I am going to plug it in right here. Yep. And as I said, you don't even see it go on. The voltage goes down to 1/100th of a volt. And so that is a good model of a dead battery. That it's not the EMF, it's not the voltage for one chemical reaction that changes. It is that the resistance changes. But of course, as you pointed out, those tie together. Yeah, a bunch of questions.
Would you be able to measure the internal resistance of those batteries by switching the voltmeter to measure resistance? Like, does that measure the internal resistance?
No, the way we should measure internal resistance is like we did in lab. You hook it to a load, you run it, and you see. What we did in lab, if you remember, is we changed our load on the outside, getting different currents so that we can figure out what this number on the inside is. There's no way I can get it from an ohm meter, because an ohm meter does the following. When you set that dial for an ohm meter, it sends a small amount of current based on a small amount of voltage. But because the battery inside can send out its own current, you would get a false reading. Because again, the meter, the way the meter reads, as if all the current and the voltage source is coming from the meter itself. That's why, as I said in class, and I should repeat it now, and I will repeat it as we go further, particularly this week, because this week in lab, you are asked to measure the resistance of many resistors. Never measure the value of a resistor when it is hooked to a circuit and a power supply. You will get a false reading, because what will happen is you will get the current that is not coming from the meter itself, but is coming from the EMF and the meter, and you will get a very false reading. So you'll see that tomorrow morning and tomorrow afternoon and the next day for those of you in the labs. Yeah.
So if there are no internal resistance, then the battery would last forever.
Well, no, okay, fair enough, but there, I mean, but okay, so maybe I should rephrase this. This is remember, the EMF voltage is not a measure of how much total energy, it's how much energy per charge. So as long as there's one more molecule ready to react in this battery, I will get an EMF of 1.5. If I could somehow magically have no internal resistance, eventually what would happen is I would run out of chemicals. You know, that very last reaction is going to take place. So no, it wouldn't last forever. It would just keep 1.5 until we got to the very last molecule, and then it's done. Yeah. Oh wow, bunch of questions. You've been waiting a while, yeah.
Doesn't the voltage use a resistor to measure the voltage? Or does it?
No, I'm sure it uses what we call a field effect transistor. Yeah. I think what you might be saying here is that when I hook this up, it almost looks like I'm hooking up another part of the circuit. And a voltmeter, fortunately, is designed so that when I hook something up like this, this resistance is about 10 million ohms. Now, I wouldn't call 10 million infinite, but it's a big number. And so there really is very little current going around this. And so there's very little added effect that this meter is doing to my circuit. And that's actually the danger of any measuring device, that if you come along to make a measurement, when you hook it up, does your measuring device affect what you are measuring? And hence, what you get as a result is not what was happening before you hooked it up. And that's always a danger in science. And if I was teaching this class 20 years ago, this would not be 10 million, but it would be more like 10,000. And that's a big problem. That's small enough that it is a problem. And so the old voltmeters were much harder to work, because you had to hook them up, measure the voltage, and say you got 3 volts. Then you had to realize that hooking up the voltage changed it, and so there was a little formula you had to work out, and say, okay, I got 3, get out my slide ruler, figure out what the true voltage is, and then you come up with 5. And so they were a bit more complicated in the, you know, and 20 years is probably not even long enough, but 30 years. So
the resistance in that battery is larger, or the new battery is the small R? Which one is larger?
So it's the small R is larger in the old or dead battery.
That battery.
Dead battery. Yeah. Yeah. Mm-hmm. Yeah.
So a battery checker from Radio Shack has a built-in resistor that measures the current, not the voltage of the battery?
Well, it's both. It measures like this. It measures the voltage, while a resistor is hooked to it. Because again, if I disconnect, I get a reading of 4.6. And I would call that a false reading because that's not the voltage I'm going to get when it's working. So a good battery tester will not just have a voltmeter, but it will then hook it to something. So you read the voltage while it's hooked up. Yeah. Yeah. Again, we're running out of chemicals. Okay? There's a bunch of chemicals in this battery. Maybe I should get to a battery that I think illustrates it a little better. Here is a motorcycle battery. It's a kind of a small version of your car battery. But what I have are these lead plates, and it's filled with sulfuric acid. Sulfuric acid conducts electricity really well. But as I use the battery, that sulfuric acid becomes water. And so now, instead of having a low resistance because I'm flowing through acid, I now have a high resistance because I'm flowing through water. Yeah.
Would temperature affect the chemicals in the battery, or would it affect the resistance of the internal?
Oh, now a little of both, I guess. Yeah, because temperature obviously does affect resistance.
So it would be working better in the cold temperature as opposed to...
It's a trade-off. And actually, most batteries work a little bit better in a warm environment up to a point. Because in the warm environment, these molecules, which have to bump and have a chemical reaction, and then after they react, have to migrate away so the new ones can come in, that migration effect is better at higher temperatures. So mini batteries work a little bit better in warm. That's why, again, if you're in the middle of a test and your calculator runs out of batteries, wouldn't surprise me at all is if you take your batteries out of your calculator, put them in your hand to warm them, shake them even, and so you rattle them around, and the idea is you are bumping them and letting the chemicals that have already reacted kind of migrate around, and you bring them in, you will probably have enough juice to finish up the test. You know, and you'll get through the test. And I've done that many times, not so much on a test, but in the days where the cameras with the flash were not rechargeable batteries that were built into your camera, but were the ones you go buy. So you go buy some batteries, you put them in, and you know, you've got this wonderful shot of your 3-year-old playing in the fountain, and you go up and you go, no flash. You take the batteries out, you shake it, you put it back in, and you get like 1 or 2 more flashes. Oh, good. Now let's get some new batteries for it.
Online, if you Google it, there's a map of the U.S. that shows expected lifetime of car batteries.
Oh, yeah.
And if you notice that in the hot areas like Arizona, you have 5 to 6 years of life expectancy. And if you go to the cold, it's like 3-4 years of life expectancy.
Ah, that's interesting. I have seen that for tires. It makes sense. Okay, yeah. So anyways, the temperature, what he's pointing out, the temperature does have a big effect. All right, well, boy, great questions. All right, but let me show you one last thing here in all this, is that now that I think you got the idea, and did I disconnect all this stuff? I'll just disconnect it so my dead batteries don't go completely dead. And that we will have them for next semester. All right. But let me do one more step. Let me take this equation and multiply both sides by I. I being the current. Now let's talk about this for a second. What would you describe that term as? Power, right? Current times voltage. So yeah, I would definitely call this power, but more specifically, power where? Yeah, this is what I would call the power from the EMF. This is the power that I am getting from the chemical reaction. This is the whole reason we buy batteries, is because we know that there is energy stored in them. We call that a chemical potential energy. And we know the principle of conservation of energy, that we could take the energy that is stored as a potential energy, in this case a chemical potential energy, and by running it through a circuit we may now get, say, kinetic energy. Maybe this is a battery that runs a little remote race car, and so the chemical energy first becomes electrical energy, which then becomes kinetic energy. And so our little race car or our airplane takes this energy from that. What would you call this? Good, power again, but power where and for what? Yeah, this is power being used up. Where? Yeah, this is what is going on inside of the battery, which unfortunately is probably doing nothing more than turning to heat, and so my battery is getting warm. And of course, if there was too much current, this could get significantly warm. And I suppose the battery could catch on fire. In fact, a few years ago, I did a little show and tell for a 5th grade class, and we were watching magnets and stuff. And they were having, and afterwards they wanted to play with it, so I just let them play. Turned around and smoke was pouring up out of the battery. You know, and so they had just short-circuited it together, and there was no resistance here, and so it was just getting hot. Same thing happened to me a couple of years ago too, where I happened to have a couple of quarters in my pocket, and I dropped a 9-volt battery in there. You might be familiar with the 9-volt ones. They have the 2 electrodes on the same side. So as it sat in my pocket, it just short-circuited like that. And before I knew it, my leg was very warm. Ow! And it had worn out my battery and short circuit. So this is the power being consumed. And I would say this is not the part you want. Because what's this? Yeah, this is the interesting part. This is the power, yes, but this is the power being used by the load, right? This is what I'm really after. What I really want to happen is I want to take the energy that is being given off from the chemical reaction and being delivered to my load. Unfortunately, that part comes along for free, and I just got to deal with it. Hopefully it's a small number, and you can see that if the internal resistance is small, it is a small number. Yeah.
Are the batteries conductors, so when they approach a certain temperature, the resistance is 0?
No.
Why?
You mean like cooling down?
Like the superconductors, they don't have resistance at a certain temperature.
Yeah.
So when the battery heats up to a certain temperature, there's no more resistance.
But you're going the wrong way. Cool down, they have are the superconductors.
Oh, I thought it was when they heat up.
Yeah, no. So I thought you were going to say, could we cool the battery down until there's no more internal resistance? Oh, sure. But you would cool them so much that the molecules would barely be moving and you would have no chemical reaction. So, but if you could get both, there you go. You'll get a Nobel Prize. You will make billions of dollars. You will donate back to the school and buy me a red Ferrari. Yeah, right. Or Tesla, you know. All right. So, but that's the unfortunate thing of the chemical reactions. Yeah, they based upon their temperature. Human life, or any life, that's the challenge of human life. I mean, if you get them too cold, right, you die. You know, if your body temperature drops, and it doesn't have to drop that much. I mean, your body temperature, normally is 97, 98? 98? Yeah, and it's just a few degrees, as you guys probably know from your biology classes. The chemical reactions that are needed to sustain life just go away. So you can't let your body core get below that temperature. And unfortunately, the reverse is true. If they get too hot, they hit so hard they fall apart. And all of our molecules that sustain life break apart into little pieces. So that's not good either. So there's a certain range that these molecules can use. Anyway, back to our electronics here. So that's what I'm trying to say here is we've got some power being delivered from the EMF. We've got some power being consumed. Part of it is just wasted heat in the battery. Unfortunately, just a natural part of life that we just have to deal with. We would like to minimize it, sure. So the best thing is to have the smallest amount of internal resistance as possible. That probably was obvious way back at the beginning. Have as little as you can. But this is where the energy goes. But watch this for a moment. If this is the energy being consumed. And the stuff I'm interested in, let me put this equation for the current into here. And I will get E squared over R plus, or little r plus big R squared times capital R. If I look then at this power, I squared R, as I change my load, okay? And so like you guys did in the lab, you took these load and you could change the dial. What would happen, let's say, if I had a small or big load? Let's go with small for a moment. Small would be like that short circuit I was talking about, the fifth graders who put the wires together, or the coin that short circuited the 9-volt battery together. How much power is being used, and I should say used in a useful sense, when the resistance is really small? Isn't it 0? So if you have no resistance, well, that means you're not consuming any energy here. Now, don't get me wrong, you're still consuming energy. No resistance would be a lot of current, right? So where is that energy?
It's going into this.
Yeah, it's being consumed here. So this is getting hot. On the other hand, what happens if the resistance is really high? You also get very little current and very little power, right? When this number is really, really big. And then that kind of makes sense too. If you had a lot of resistance here, that means very little current would be coming. And your energy being consumed here, part of it is how much current do you have? And so if you really wanted to run something up here with full power, I'm trying to point out is you would not want to adjust this resistance to be too high or too low. If it's too high, you get very little current. But if it's too low, yes, you get a lot of current, but a lot of current means the energy is being consumed where? Yeah, in the battery. For those of you in the audio world, this could be your amplifier. This could be your speaker. And when you hook an amplifier to a speaker, if this speaker has too much resistance, it won't play sounds very loud. Not a good speaker. But on the other hand, if this is too low, what happens? Yeah, you still don't get a lot of power here, although you get a lot of power here. So what happens to your amplifier? It overheats and burns up, just like the battery in my pocket. And so either one of those is not your best situation. So what is the best situation? If I were to plot this, it would look something like that, right? I would get the most power when my load resistor is equal to what? And I hear some of you say internal resistance, and you're right. But why do you say that? Yeah, and hopefully because you read the book and I got the answer, But we can see that in the math here. Let's take a derivative. Let's look at what we would call the maximum power of our load. We have an equation. If this was a math class and I asked you, how do you find the maximum of that function, what would you do? You take the derivative and set it equal to 0. So I'm going to do exactly the same thing. I am going to take the derivative as the value of the load resistor could be adjusted. Again, if this was audio equipment, I would go back. Here is my amplifier. Here is my speaker. I could hook a 4 ohm speaker, an 8 ohm speaker, a 16 ohm speaker, a 32 ohm speaker. I've got different options of my speakers. In fact, then I can hook my speakers in series and parallel, so I can get 2 ohms, or I could get a whole combination of different resistance from my speakers that I want to hook up. This is my variable. I can hook it any way I want. But if I really want those speakers to be loud, there's only one way to do it best. Because too much resistance, they're not loud. Too little resistance, they're not loud. And worse still, they burn up my amplifier. And so what is that value? And so you can see that if you take a derivative and set it equal to 0, we will find the peak of this curve. where is the slope equal to 0. So derivative and set it equal to 0. I like to kind of write it as a product instead of a quotient. I will bring the EMF squared out in front, but if I write it as this, I think it's a little bit easier to take the derivative of a product than a quotient, so I will. And so it would be first times the derivative of the second, and then the chain rule just gives me a 1, plus the second times the derivative of the first. And so that becomes 1 over r plus r squared. When I leave that term, I'll bring this to the other side. It becomes a plus 2r then in the numerator, and an r plus r, or little r, big R added together, divided by 3. Fortunately, 2 of those cancel with 2 of those, and so I get r plus a big R is equal to 2r, and then r becomes equal to r. And so those of you who said, yes, you are going to get a particular value, and you're going to get your maximum power when your internal resistance and your load resistance are exactly the same. And that's more time than I thought I would take on this, but it's a whole idea of what we call the maximum power transfer theorem. And again, this is an audio amplifier. We can adjust our speaker arrangement so it matches this. And so many amplifiers will say on them purposely, what is their internal resistance? Are they a 4 ohm amplifier, an 8 ohm amplifier, a 16 ohm amplifier?
Is this related to like Thevenin equivalences and stuff like that?
Well, I suppose so. I mean, the Thevenin resistance you could think of as an internal resistor. And so if I had a circuitry that had many resistors, and then I came down to the Thevenin resistance, and I wanted to use that to transfer the maximum power, I would know what I want to hook up has to have an equivalent resistance to the Thevenin resistance. Yeah. But the Thevenin resistance is used for a lot more other things than just what's the maximum power transfer. But that would be, yes, one example. Yeah. All right, well, as I said, it took me a little bit longer there than I anticipated. Let's look at some problems then in the book here. Let's look at some of these. I did a lot of what I would call kind of your standard ones. And so I picked some in the back of the book that were just a little bit different. Not to say that the ones that I've done for you already weren't important, because they are. It's just that I want to make sure you see as many different types as we can. So the first one I put on my list, I believe, number, I'm going to say 5. Yep, number 5. Your author does a good job of giving you a picture, so I will do that. And go to chapter 28 and look at problem number 5. This will take us all the way back to the beginning of this chapter. In fact, given all the problems we've done, I almost think this is one too easy, but probably good to go back and do probably the easiest one you will find here in the chapter. And here's what it says. It says, change my receiver here. But it gives a little circuit here, and it shows it, hopefully here in number 5, and it says, find the equivalent resistance between points A and B. Then, part B says, a potential difference of 34 volts is applied between these. Calculate the current in each resistor. So the beginning part of this chapter was about equivalencies and how we can take a circuit and make its equivalent. And so what they're saying here is we are eventually going to hook up a 34 volt battery to a situation that looks a little bit like that. And so the first part is just what is the equivalence of this. Hopefully you will notice right away something about the 10 and the 7. What do you see about the 10 and the 7? Yeah, and so the first thing I would do is replace the 10 and the 7 with its equivalence. And in this case, its equivalence is the reciprocal. So 10 reciprocal plus 7 reciprocal equals reciprocal of that. And so it's about a 4.1. And so this is 4.1. 17? No, that's if you add them. That's what you do in series.
These are resistors.
These are resistors, not capacitors. Right? So this, okay, maybe I should write it here. So it's 1 over R1 plus 1 over R2 is 1 over the equivalent. Okay? And so I did the harmonic sum there to get the equivalent. Now the other two I haven't touched yet. There's a 4 and a 9. And so the next circuit would be the equivalent of this circuit. And how would you say about those three resistors? They're all series, which we would then add together. So does that make 17.1? Oh, maybe that's what you were saying, were you? You were saying the total 17?
No, that's confusing.
Oh, okay. All right. So 17.1 does come out to be the overall equivalent. And so we started this chapter with that one way of solving these problems is to find the equivalence, because the equivalence can be helpful for finding the current in the real circuit. I also pointed out not every circuit has an equivalence, so you got to be careful with that. You can be series, parallel, or neither, and then that's when we got into Kirchhoff stuff, which we'll see that next. But this one is an equivalence one, and I claim that it becomes very useful because this is the answer to part A. What is the equivalent resistance? Part B then says, what is the current in each of these? Okay, well, taking this right here, the current would be 34 divided by 17, actually 17.1, so it should be a hair under 2. 34 divided by 17.1 is 1.99 amps. And as I said with the capacitors, I even said last week, I'll say it again, the equivalent circuits are nice only if they help me with the real thing. So never forget that they are just equivalencies. And of course it does help me with the real thing. If I know that there is a current of 1.99 amps, what does that tell me in the real circuit? Yeah, it tells me that there is 1.99 amps in that first resistor of 4. So there's 1/4 of the problem already solved. What is the current in the first resistor? I can also get another quarter by noticing this, that 1.99 amps comes along here to this node and splits. So there's less than 1.9 in each of those, but they regroup and come through there. So how much goes to that one? 1.99. So that's why I can get half the problem done already by looking at this equivalent circuit. So there's the nice thing about an equivalent circuit. I can find out how much current is in 2 of those 4. Now the other 2, I got to give a little bit more thought to. And the choice is kind of ours on how we want to do it. You can take different approaches. I kind of like the approach of, couldn't you tell me how much voltage there is across that resistor now that you know the current? Yeah, you already know it's 4 ohms and now the current is roughly 2. So isn't this 8 volts or a fraction under 8? And likewise, couldn't you tell me the voltage here? Because the resistor is 9 and the current is roughly 2. So isn't that 18 volts? And the reason that is helpful is because to go all the way around the loop, doesn't it have to be 34? So if I go 34 and subtract an 8 and subtract another 18, this must tell me what needs to be left for my middle ones. Which is what, by the way? 8? Eight times 3, 24, yeah. So that must be 8 volts there. Now, maybe it would have been easier for this case to come back to this equivalent circuit right there. That equivalent circuit is about 4 ohms, 4.1, times my current of a hair under 2 would give me 8 volts right there. And so whichever way looks easier for you, I would encourage you to try both so that you can say, look, this is telling me that there's 8 volts on this equivalent. But for that matter, when I study the real circuit, it tells me that there is 8 volts. Either way, I have 8 volts. And the reason that becomes helpful is because if I look at, say, this lower one, the current would be the voltage, which is 8 volts, divided by its resistance, which is 10. And so that's 0.8 amps in that lower one. Which means that this needs to be 1.2 amps because that 0.8 and that 1.2 have to add up together to give me 2, right? And so I'm done with the problem. Although I could also get the top one using Ohm's law by saying its current would be V divided by R. We just did the 8 volts. The resistance is 7. And that would be, oh, that's not quite 1.2. 142857, repeating indefinitely. You gotta love prime numbers. Nothing better than 1/7. It's gotta have 6 digits, repeating indefinitely. Oh, yeah. But it's good discussion if we were in math, but we're not. All right. So, but there is 1/7, and a little bothered that it's that far off. Is that just rounding? Okay. Okay. So it is just rounding. And I was trying to go quick. But I just wanted you to see what I think should be the easier one. Maybe not. But that's one way and one approach of the type of problems you are going to get. Let's look at number 17 then. I'll pull up the picture and we'll just, spend the balance of time seeing how much we can do in terms of a lot of different circuitry. But I'm hoping that you will see the point of this chapter. There really was no new physics in this chapter at all, but it was an applied chapter. It was take our idea of capacitors, take our idea of conservation of charge, take the idea of conservation of energy, put them together and build some circuitries, make certain amount of currents happen in a certain pattern. And so this one has 2 batteries and 4 resistors. And so what it says here in 17, where to go here? It says determine the current in each resistor. Well, there's a question. Do you want to use the Kirchhoff's loop and voltage rules, the conservation of energy or conservation of charge? Or do you want to do equivalencies? But remember, not everything is equivalent. Remember, it's series, parallel, or neither. So do you see anything in series and parallel? Actually, aren't these 2 in series? How about these 2? They're series too. But as you will hopefully see after that, we're stuck. If I take the 8 ohms and put it here, and then I take the 1 and the 5 and put them together to make 6 ohms in this little branch that has a 4-volt battery, And the other one, if I put those resistors together in the branch that has a 12 volt battery, that 1 and 3 become a 4. So I can kind of get started with equivalencies, but I can't finish the problem that way. And so you may choose to do a little bit of equivalency and then realize I can't go all the way. Or you may choose, I'm not even going to mess with any equivalency then if I can't do all of it, or whatever you want to choose. But I do think a little bit of equivalency can be useful. You can take something that looked like 1, 2, 3, 4, 5 different resistors with 5 different currents, something down to now we only really about 3. And of course now it looks like the example I gave you when I did the first Kirchhoff's law. I had 3 loops or 2 loops, side loops, and then 2 batteries. And that's because of those batteries is why I cannot put these together. And as I was mentioning, if you tried to draw a wire from here to here, something like that, all of this in green would be 1 voltage. But then the other side would be, say, red. It doesn't go all the way to either of these resistors, so you would not say those have the same voltage, and likewise you wouldn't say that those have the same voltage. And they certainly don't have the same current. So here's a situation where we have the neither. And it's because of that, then, we need to write these out. And so, as I was mentioning, maybe the thing to do is to start here and call this current number 1. Now, I start there only because it's a bigger battery than any of the other ones. And so, my guess, and as we pointed out, purely a guess, maybe an educated guess, so it's maybe more of a hypothesis by saying, I think the current's going to go that way. But remember, if I come up with a negative number, that just means that the current is actually the opposite of the direction I chose. So it really doesn't matter. Okay? What matters is you make a decision on what you're calling the positive direction. Okay? Now, this current, as it goes through the 4, would have to go through the 6. If it still had more than 4 volts, it would overcome this battery and the current would go this way. But if it didn't, the current would go that way. So I'm not really sure what's going to happen here, but I'm quite sure that on this side, which I will call current number 3, it goes around that way. Both batteries are trying to send current that way. So I'm pretty sure about that one, and I'm pretty sure about that one. Not sure about that one. Yeah, so I'm going to pick a direction and go with it. Oh, number 2. And I think that 12 volt battery is going to have a lot of power still left over. It's going to overcome that 4 battery. It's going to send it the wrong way, and this battery is end up absorbing energy. This is charging. Hopefully it's charging and not just heating up, but somehow it's absorbing the energy of the current flowing in what I would call the non-natural direction. It's like a ball on a hill. We are pushing the ball up the hill. It doesn't naturally want to go up the hill, but if you add energy to it, you can make the ball go up the hill. Leave it alone and it'll go the other way, but we can force the ball the other way, and we are. And then we can write out our loops. And so, if we do, and this was, again, why I wanted to repeat this, I would suggest do the small loops. We have 3 unknowns, current 1, 2, and 3. We need 3 equations. And so pause and ask yourself, how many equations are you going to get from your loops? You will get 2 independent equations. In other words, the big loop is nothing more than the sum of the left and the right loop. And so I will just do the left and the right loop. That'll give me 2, which means I'll need 1 more from the junction rule, which is perfect because I can get that too. But here is my 2 equations going around the loop. Okay? And so I will do this left-hand side first. Anybody care where I start or which direction I go? And I really ask it, does everybody realize it doesn't matter where you start or what direction you go? That's the most important. All right, so shall I start here and go around in a clockwise direction? All right, because I've been doing a lot of that. It's totally opposite of what the battery is doing, so it kind of bothers me, but I can do it. And so I will go and realize that there would be a voltage change of 8I3 right there. My question for you is, would it be an increase or a decrease? Increase. And why? Goes against the current. So again, remember that this analogy of current flowing like water in a creek, if you are in the creek and you are hiking in the creek and you are going against the flow, which way are you going? Uphill, right? And so you are definitely going uphill. All right, so I'm going to put a plus. This is an increase in energy. Maybe I shouldn't label plus minus. That can get even more confusing. All right, so we'll just say we went uphill. As I go over to here, there would be a change of voltage. According to Ohm's law, it would be 6I2. But again, I think the harder one of it is it an increase or a decrease? Decrease. And how do you know that? You're going with the current. So again, think of this as an analogy. You are in the wire. You are in the creek. You are on a hike. You are walking through the creek. Splash, 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 splash. As you go with the flow of the water, you must be going downhill. All right, so there it is. Here to here would be a change of 4. Plus or minus? It's a minus. How do I know? Okay, I'm going to a lower potential. How do I know I'm going to a lower potential? There's a smaller little line, right? That's what we mean here. The small line means lower energy. This means higher energy. Notice it has nothing to do with the direction of the current. The direction of the current is a discussion we have for resistors, not a discussion we have for batteries. The voltage is determined by the chemicals and the way the chemicals are laid out. Okay? And of course, we now have completed the loop, so there is equation number 1.
So there's no I in equation?
No I. The voltage is 4. Right? You get 4 from the chemical reactions, whether there's a little bit of current or a lot of current. If I go to the other loop, and maybe again, I'll start in the lower left-hand side again, and I'll just do the same kind of clockwise thing. If I start here and go this way, there is a change of voltage of 4. Plus or minus? Plus. I go from the little line to the big line. Then there would be a change of 6I2. Again, there's Ohm's law. I'm going through a resistor, so it is resistance times the current. But I think the harder one is not Ohm's law, but is it a plus or is it a minus? It's a what? It's a plus. Why is it a plus? I'm going against the current. Remember, we labeled the current going this way, so if you are going down a little hike, you are walking through the creek, splash, 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 you are going against the current. Plus. I continue on my little hike and I eventually get to this resistor. According to Ohm's law, it would be its resistance times its current. So there's the voltage change. But is it a plus or a minus? It's plus. Why a plus? I'm going against the current as I splash through the water. So again, okay, make a mental picture of you walking through the water and which way is the current flowing as you are walking through. Finally, we get to this other battery, which would have a voltage change of 12. Has nothing to do with the current. Has nothing to do with the direction of the current. Is it a plus or a minus? Minus. How do I know that? That's what we mean by that labeling. We mean one is at a higher potential than the other, and we went from the big line to the small line. Okay? And so we are walking from here to here. Big, little. Okay? And then, of course, we have completed the loop, and so that must equal 0. Yeah? Yeah, so small to big is why I have a plus 4. Big to small is why I have a minus 12. Yeah, good. All right. And so, again, you got to pay attention to whether are you changing the voltage due to a battery, or are you changing the voltage due to a resistor? If it's a resistor, it's Ohm's law, and then you look at the plus or minus based on the current. If it's a battery, you change the plus or minus based on just the chemicals, so it's just given to us, and then the plus or minus depending on whether big line to small line or small line to big line. Well, I need another equation. What would my other equation be? Yeah, this is the node rule. These two were the conservation of energy, and we have 2. We need 1 more, which is perfect, because if you look at that node, hoping you can see, doesn't current number 1 come into that joint right there, that node? And then what happens, it splits, and some of it goes this way, which I called number 3, and some of it goes down this way, which I call number 2. So my third equation would be I1, what is going in, must equal what comes out. Right? And so there are my 3 equations, 3 unknowns. And of course, now I would do a little arithmetic to find out what is the current. But in the interest of time, let me jump to number 32 and see how many I can kind of hook up here. This one hasn't had a capacitor in here, and I believe 32 does. And so let's look at one that has a capacitor and has a capacitor hooked up a little bit different than anything we've done in class, but nothing new that you couldn't figure out on your own. Physics is about knowing how to apply a few fundamental ideas to a universal phenomenon. So we could put this capacitor in any kind of crazy situation, right? And you can figure out what the current is, in theory. And so that's what this one is all about. Let's look at number 32. 32 does have a capacitor, a battery, a switch, but I think they've got a little more complicated here. We've got 2 resistors with the switch up there. And so when I look at this and I read the description, it says, look at the circuit. The switch S has been open for a very long time. It is then suddenly closed. Determine the time constant before the switch is closed and B, after the switch is closed. C, let the switch be closed at time equals to 0. Determine the current in the switch as a function of time. Well, let's start with just a discussion about this circuit. It says leave the switch open for a very long period of time. All right, so if I leave this open for a very long period of time, what are you going to notice? Actually, no, the battery won't die. What will happen to that capacitor? It will fully charge, and then what will happen? No current will flow.
Well, you have to realize that the voltage drop across the resistors will be a little less than you expect.
Well, hopefully the current will stop flowing, and then there won't be any voltage change. So I'm going to leave that circuit up here, but I'm going to do something that may not have grabbed your attention immediately. Look at the 50 and the 100. With the switch open, are they in series, parallel, or neither?
Series.
They're actually in series. I know they've got a capacitor between them, but series means they have the same current in them. And so couldn't I replace these two as its equivalent? And so what's the equivalent? Yeah, and so this is 150, are we kilo up there? Kilo. Okay, so this is 150 kilo ohms. And so I claim that when the switch is in the open position, that circuit I have up there is equivalent to that one. Right? And so I have taken something that looks a little more complicated in the sense it's got a switch and 2 resistors, gotten rid of the switch, gotten rid of the 2 resistors, and isn't this what we've been studying? Isn't this why I started today's lecture and finished last time? Could you tell me the equation for the current and the charge on the capacitor here? Isn't the charge on the capacitor CV1 minus e to the minus t over RC, right? Isn't that what we worked out? Let's not work it out again. But what I've done is I've taken what I've already know, I've looked at this, and I've taken that circuit and got the equivalence of it. And the equivalent, 1 capacitor, 1 resistor, 1 battery. I know the solution to that already. And so that's why this becomes a fairly easy first question anyways. When it asks, before the switch is closed, what is the time constant? This is the time constant, RC. So the R is 150 kilo. The C is 10 micro. If you put those together, what do we get? 1500 milli, 1.5? I think I did that right. 1.5 seconds. So the time constant is 1.5, which meaning this thing would build up to 63% of its full charge in 1.5 seconds. Okay. But then the second part of this, B, says, what is the time constant when the switch is closed? Of course, a little harder, but I'm hoping you'll see. What happens when the switch is closed? Yeah, if I close this switch, I would kind of see this as this capacitor now is discharging. Of course, this power supply is now sending current through that way. But the point is the capacitor is discharging through only the 100 ohm resistor. And so now I have a different time constant. And so the rate of charging and the rate of discharging are a little bit different for this circuit. In the same thing like they would be in the flashers of your car. You would turn on the flasher and then you would have the light go on. When the light goes on, the resistance is different when the light goes off. And so the amount of time that the light is on and the amount of time the light is off are different because the resistance is different based on the temperature of the bulb because the current is going through there. And so as your blinker flashes, you don't get the same amount on as off. There's a different time constant involved here. And that's what we see here. So where this is A, B is the same idea. It's just now we're going to have 100 kilo times 10 micro, which I think comes out to be 1. Is that right? 1, 2, 3, 4, 5, 6. Yeah, so all that is 1 second. And so the rate of discharge is a little bit different than the rate of charging up. Kind of makes sense. Charging up had to go through the 2 of these resistors. And again, notice I solved this by taking what I already knew about one capacitor and one resistor and switched it into that. Which now, the last part of this, C, is hopefully straightforward. What is the current through the switch?
The sum of both current.
Right, if I were to do Kirchhoff's rules here, I would get a current through this way, and I would get a current through this way. But this is real easy to get the current, right? I mean, wouldn't the current in this one be nothing more than 10 volts minus what I will call current number 1 divided by the 50 kilo ohms equals 0. And so current number 1 becomes 1050 divided by kilo. 1/5 is 0.2 kilo. It becomes milli when it's in the denominator. And so we're looking at a 0.2 of a milliamp flowing through this resistor, which then is also going through the circuit and back around, or the switch and then back around. But that's not the only thing happening in the switch. What's also happening in the switch is I've got a discharging capacitor. And if I were to write out the equation for that one, I would have Q over C minus what I might call I2R. And that R is 100 kilo ohms. And you can solve this one if you want, but haven't we already done that? Isn't that the equation for a discharging capacitor? No, it does have 10. Maybe we should come back to here. What is going to happen in this first equivalent circuit? When you leave it open for a long period of time, what eventually is going to happen to this capacitor? It's going to build up until 10 volts. And then there's not going to be any more charge flowing. Now, it could have been wired differently so it doesn't get to a whole 10 volts, which is the next circuit. If we get that far, I'd like you to see that one. But this one is hooked up so that capacitor will get up to 10 volts.
I was just that I thought when it comes to resistor.
Only if there's current. If there's no current, then there's no drop, right? So after a long period of time, there's no more drop. Yeah. So this would be the 10 volts from what the capacitor builds up, divided by the resistance of 100 kilo times e to the minus TRC. And so this is 0.1 milliamps times e to the minus t, and then the time constant. Well, the time constant we already did back here, right? That's a 1. And so the equation I have is 1/10 of a milliamp e to the minus tc. So the total current in the switch then becomes my 2 milliamps plus my 1/10 of a milliamp e to the minus t. There we go. And so that's the current in the switch. Current coming from the battery and current coming from the discharging capacitor.
The main power source was cut off when we were finding those.
Yes. Oh, no. I wouldn't say it was shut off. When this switch was opened, then this power supply was like that. And it wasn't shut off from there. That was building up charge.
But then as that is discharging, wouldn't the power supply replace all the discharge charges?
Oh, are you saying this would go like that?
No, what I'm saying is that when we found port A,
Yeah.
the time it takes for it to discharge,
Yeah.
port B, the time it takes for it to discharge, but as it's losing power, the voltage source will replace the power on it, so this will be like infinitely low, just like charging and discharging at the capacitor.
If I understand you right, I would say yes, but I would say that's what I did. Let's talk more, but let me show you at least one more, because some of these little switches can get a little interesting in their shape and their pattern, and I think 46 is at least worth. Is it 46? No. How about 61? Yeah, 61 is at least worth looking at and setting up, because I think this is what you were referring to when you said maybe the capacitor doesn't charge all the way up to 10 volts. Although now that I mentioned that, I think you were saying that just because you thought the resistor would have some. Look at this one. And we're not going to have time to write out necessarily the equation here, but what do you think would happen when you close that switch? Right, you should get, let's just look at this loop for a moment. If all you did was look at that loop, and bummer, I'm not going to have time to solve it, but if you were to look at that loop, couldn't you find the current as a combination of the current that is feeding into here plus the current that's feeding into there? So I maybe better write it out. Crap. I would write the first equation then as 9 volts minus 12 kilo I1 up here. Then I would write it as minus 15 kilo I2 equals 0, right? And so what would happen is there would be more current in here than in here as this is charging up. But after a long period of time, what's going to happen on this section? No current, right? This capacitor is going to build up to some voltage. And what I want you to see is not 9 volts. When it builds up, so no more current is flowing here, wouldn't I1 and I2 be the same? So after a long period of time, current 1 and current 2 are equal. And so we would have 9 divided by 27 kilo, right? That's how much current would be flowing through here. Now the reason that's important is because if I know the current, if I then take this resistance times that current, wouldn't that tell me the voltage from here to here? And isn't that only going to be part of this? And so from here to here, looks like, I'm not real sure, but it looks like it's going to come out to be about 5 volts. So this capacitor would build up to how much voltage? 5, right? This would have to be the same as this, right? And that's the key to this step, that you would realize that this capacitor does not build up all the way to 9 volts. This capacitor would build up only to whatever the math works out, which would be roughly 5 volts. Once you know it's 5 volts and you open this circuit, then I think the easy part begins. What happens now? The capacitor discharges. These two are in series. Put them in series and you have one capacitor, one resistor. You know the equation for a discharging capacitor. The hard part was to realize that that capacitor does not charge up to 9 volts. It charges up only to 5-ish. Right? All right, well, good luck. We better move on to magnetism. And then figure out a good test date too.